One day you find yourself betting a sleepwalking alien that you'll be able to estimate how far away he will be on average from where he is now if he walks for 5 minutes and then returns to the place where he first was to walk again for another 5 minutes, on and on. If you fail, good luck escaping a UFO. At first it sounds stupid. The alien is sleepwalking. In fact, he is experiencing what's called a random walk. That is, every second he takes a step of length L in a random direction. So if his movements are completely random, how do you expect to know how far he'll walk? Luckily, the alien can only walk left or right. So, like when you flip a coin, there are only 2 equally possible outcomes. Even if on the first run he ends up to the left of his origin, over many walking trials the deviations will cancel out, and on average, he'll not have displaced at all. That's the answer to a one-dimensional random walk problem. But what if the alien stepped every half of a second instead of every 1 second, every eighth of a second? At a certain point, the alien's actions can't be described discretely anymore. They become continuous because the points are separated by time differences too small for us to characterize. This continuous random walk forms the basis of Brownian motion, one of the most fascinating ideas of physics. In 1827, botanist Robert Brown noticed that pollen particles suspended in water seemingly jiggled for no reason, and Brownian motion was born. Newton's second law says that force equals mass times acceleration. These pollen particles accelerated in every which way, so there must be some force acting upon them in every which way. Einstein figured out in 1905 that these forces must be exerted by water molecules colliding into the particles. So he proved that molecules exist and demonstrated how Brownian motion can affect something as integral to life as molecules. What does this discovery tell us about Brownian motion? Well, we know Brownian motion is a continuous random movement, but there's more to the story. Whereas solids have atoms that just sort of jiggle in place, fluids, or liquids and gases, have much faster and more spread out atoms. That's how solids hold their shapes while liquids like water float. Fluids atoms, due to their greater moving abilities, are far more likely to bump into things surrounding them than solids atoms are. So Brownian motion is a continuous random walk, yes, but one carried out by a particle only when it's supported in a fluid. Now, one of the most prevalent ways Brownian motion affects you is through diffusion, or when particles move from areas of high concentration to areas of low concentration. When you saw the alien, you saw him not just from the way he walked, but you also noticed the way he smelled. Who knew aliens were so stinky? But you weren't even near him, so how was he so pungent? Diffusion. The air was already full of oxygen and nitrogen molecules, but when the alien left his UFO, the stinky particles from his breath joined the air outside. Suddenly, the space around him had more particles and molecules than the space around, say, where you were. This is where diffusion and Brownian motion collide. Pun intended. Now, due to Brownian motion, the stinky breath particles from the alien moved randomly as they were bumped into by air molecules. The more molecules and particles there were, the more the particles were bumped into and the likelier it was for them to leave the alien's vicinity. But wait, you say, didn't you tell the alien that he won't have moved at all if he was walking randomly in symmetrical directions? Sure, but that was on average. Now the breath particles aren't going back to their originating point after a set amount of time. They keep moving. Now when one particle reaches a patch of air that others haven't yet reached, it will undergo relatively smaller Brownian motion because there aren't as many particles and molecules around to bump into it as there were near the alien. Soon more particles will move to this patch of air and the cycle renews until the concentration of breath particles is even everywhere. Because of Brownian motion, these stinky breath particles suspended in gas were able to diffuse to assault your nostrils. And Brownian motion is useful for more than just sleepwalking alien encounters and pollen rings. For example, stock prices are expected to go up over time, but there will always be random fluctuations or Brownian motion due to outside factors. Dust motes dancing in sunlight are also undergoing Brownian motion because the air molecules around them are constantly colliding into them. And when a rocket launches, it doesn't go perfectly up. It undergoes Brownian motion thanks to random gusts of wind. Stars or black holes also experience Brownian motion due to gravitational forces of smaller nearby objects. Now you know a bit about what to expect if you ever travel to a galaxy far, far away. And if you do, you know you will always find at least one friend that you met thanks to Brownian motion.